Now, yesterday I started off looking at this containerization stroke virtualization topic, and I just want to finish these slides here this morning, and then you have enough detail to be able to tackle the lab here on the right. My Wi-Fi isn't behaving that good this morning, so it's very slow to. There should be images popping up here, but you know the layout of this website anyway. So I'm going to bring up these slides here and pick up the story where we left off yesterday. And so I started talking about virtualization, which is, I would suspect, a topic that you have just some familiarity. I shouldn't have mentioned the network because I think it's just biting back at me. So you can see my screen now, I'm thinking, and let's bring up the slides again. So as I was saying, you are familiar with virtualization from a practical perspective, if not from the full theory perspective, and that's fine. And what in terms of using virtualization on your own personal computer, the advantage it gives you is that you can have multiple operating systems. If you're experimenting with different operating systems, you want to install utilities and packages that only run on certain operating systems. It gives you the opportunity to essentially work with any software that you want to, uh, even if that software is OS dependent. From a cloud perspective, what virtualization allowed cloud providers to do was to offer to organizations the ability to run those organizations' their applications in an isolated environment. And so each organization's application would run on a virtual machine on top of the cloud provider's hardware. And then the organizations would be content that their applications cannot in any way be content from a secure point of view, I suppose, really. So that was great when all we had was virtualization. The downside of virtualization, though, is that it's quite what we say is that it's heavyweight. Heavyweight really means that each virtual machine running on top of your hardware consumes a lot of the hardware's resources in terms of CPU power, RAM, memory. That's really what we mean in terms of being heavyweight. So it's kind of not cost effective. And that's where containerization stepped in. So that's kind of where we left it off yesterday. And so with containerization, uh, uh, from a stack point of view, just give me 1 second. From a stack point of view, I'm showing you on the right there, you have your hardware at your base as always, whether the hardware be your own personal PC or a data center stroke cloud provider. Now, there can be a host operating system running on top of that. There doesn't have to be though. The next layer is the really important one. You have some what we call a container engine. I suppose that's the equivalent of the hypervisor in the VM world. And then you run your applications on top of your container engine. But an application in this case now only comprises of the actual source code, any third party dependencies that it has, libraries, um, utilities, configuration files, that sort of stuff. So, there's less from a pure size point of view, there's less now to an individual application than there was in the VM world. And also, each of these are what we now call containers. Each of these consume less resources than their VM equivalent. It's also Let me just bring up my pen. Let me bring up my pen. Sorry now, I'm just trying to refamiliarize myself with the keyboard shortcuts. It doesn't do that for me. Let's try again. No, doesn't like it. Okay, let's keep going. Where was I? Oh, yeah. The the physical size of a container is smaller. It's much quicker to boot up a container than it would be to boot up a VM and load up the VM with the various parts of your application. So it has, and hence containers are much more lightweight than their VM equivalent. Down at the last bullet point there, I'm saying that containers are disposable or ephemeral. It's a, kind of ephemeral is a word we use quite a lot in this whole space. Ephemeral kind of means that the time to destroy and recreate a container is very short versus its VM equivalent. My God, my PowerPoint just doesn't want to behave. Okay, and you see the stack on the right. Now, in reality, it's not as if we've thrown away virtualization. In reality, containerization is often built on top of virtualization, certainly in the cloud world. So the image on the right there is typically what actually happens on a cloud provider platform. You have your hardware at the very bottom layer. You've got a hypervisor. You've got VMs on top of the hypervisor, and then within the VMs, you can have your container engine. Okay, it says Docker engine here, but Docker is just um, a particular instance of a container engine. And then you have your individual containers containing your applications running on top. That's often what happens behind the scenes. On your, on the left then is how you might actually have a containerized environment running on your own PC. And in fact, that's what you will have. So it's kind of not an either or. Uh, Benefits of containerization, I've kind of already alluded to them in passing, kind of portability. Once you've got the container engine installed on a machine, you can run any container. You do not have to install anything else other than the container engine itself, because the container instance will contain everything that the application needs to run. All of the third party dependencies, any configuration files, any operating system utilities, they will all be contained within the container. And so the host operating system doesn't have to worry about, does it have certain uh, packages installed in order to allow your application to run within the container. So they're highly portable, highly scalable. Scalability will come in the form of creating multiple instances of a container. If you think in terms of the global sense now, you've got an application that's running, let's say, on top of the AWS or on the AWS cloud platform environment. You've got an application that has been containerized, as we say. Now, rather than having that containerized application running on one piece of hardware, you would actually make multiple copies of it running on different hardware provided by the cloud provider. So there might be an instance of the container running or maybe multiple instances of the container running in the US region of AWS, number of instances running in Europe, more instances running in Asia, et cetera, et cetera. So it can be, that's how we achieve scalability essentially, right? Well, it's one way of achieving scalability. And that kind of works really well because creating multiple instances of a container is going to be it's going to occur very fast because of the reasons I mentioned earlier on. Cost effective, I kind of already alluded to that. The self-contained idea, this is, I kind of mentioned it in passing. Once you've got the container engine installed on your hardware, then the host operating system doesn't have to have any other special installations in order to ensure your application runs properly. The application within the container will contain everything that it needs. And we'll see that as we work our way through this. You have the same sort of isolation. You have the same isolation with containerized applications versus VM applications. So each, going back to here, like each of these applications are, you're guaranteed that they are isolated from one another. They cannot in any way kind of communicate with one another over a network unless you want them to. Okay. But you have control over that. This just summarizes the difference between virtual machines and containerized. And I've kind of mentioned them in passing, so I'm not going to go through this one by one. You can scan over it yourself. Suffice it to say that, to repeat myself again, the containerized approach is much more lightweight solution than the VM approach. Now, from a technical point of view, there are two, let's call them constructs, that you need to be able to distinguish between when you're talking about containerization. First of all, we talk about images, and these two, there's images and there's containers, and these two are interlinked, but they are different things, if you like. So an image, I'm saying, is that's essentially a packaged version of your application. It's executable. It's a packaged version of your application, and within that package is everything that your application needs in order to run. And I've kind of itemized them here. Clearly, inside the package will be the application code of your application. It will be any third-party dependencies. So if your application was a Node application, for example, the application code would be JavaScript or maybe TypeScript. The dependencies would be all those NPM packages that are required by your application code. Any other system tools that may be needed, utilities, any libraries that may be required, any configuration files, all of that is packaged within what we call an image of your application. And these packages, clearly, there's a way of creating these packages. So an image is kind of it's a static thing. The other point that's important to be aware of, I'm saying here, is that essentially inside in a package is the entire file system that your application needs in order to run. And we'll see that later on. So that's an image. Then the other construct is a container. Now, what a container is it's the actual runtime instance of an image. Yeah. So what you execute is a container. And what is the container executing? It's essentially executing the contents of an image. So a container is a runtime instance of an image. Down at the low level, it's really an operating system process. At the OS level, everything really boils down to what is happening at the OS level. So it is really an OS process, but it's completely isolated from all the other operating system processes, and maybe the other operating system processes are running other containers. A container's file system is essentially the file system that you have created within the image. And you can control that. If you want to make an analogy with object-oriented programming, we know in object-oriented programming we have classes, and an instance of a class we call an object. Well, to make the analogy, a class is like an image, right? It's a class is a template. We often refer to it as a template for an object. Well, in the containerized world, an image is the is a template for an instance. Sorry, a template for a container. So, so a class is the equivalent, or an image is the equivalent of a class, whereas a container is the equivalent of an object in the object-oriented world, because an object is a runtime construct, if you like. That analogy is fine initially, but it kind of breaks down after a while. But as an initial kind of idea, uh, it might be useful to equate those two worlds. Now we'll see much later on in this module, not straight away, we'll see how to create images of our own applications, because you can create an image of any type of application. And we'll see how to do that. A lot of the earlier part of this module will be focused mainly on sort of how do we create containers and run them and play with them and that kind of stuff. So that's the kind of overview of containerization. So what actual containerization platforms are available to us, and for sure the dominant one is a platform called Docker, which I'm sure you've heard of. So Docker is what we call a container engine. It's open source, roughly was released around 2013, I think. And it's an open source platform for both creating images and also creating containers for managing both of those constructs. Okay, so it does everything for us. That's all right. That's just a general point. Okay, this is kind of nice stuff to know, but not really essential. It's actually written in a language called Go. And initially, the Docker container engine only worked on the Linux platform. But fortunately, today we have something called Docker Desktop. And with Docker Desktop, you can run uh, the Docker container engine on any operating system platform, including Windows and Mac. So I did mention to you yesterday that, and I gave you a link. I mean, if you Google Docker Desktop, you'll probably get the same link that I provided. You can each of you needs to install this Docker Desktop. It's really just it's an application at one level. It's a application that you install on your personal computer. Internally, the Docker Desktop, internally, it actually uses virtualization. It creates a small Linux virtual machine within um, internally, but you don't have to worry about that. You won't be interfacing with Docker Desktop as if it was a VM. You'll just be interfacing with it as you would like any other application. And architecturally, here I'm just showing you what the architecture of this Docker, of Docker itself, and by implication, kind of Docker Desktop. So the Docker container engine is essentially a client server architecturally. The main part of the server is what's called the Docker daemon. So that's the bit that does all the work for you behind the scenes. And the Docker daemon, it manages any local images that you might have, whether the local images are your own or they are images that you acquired from some remote repository. It also, Docker, the daemon, it manages the creation and execution of containers. So it's both a container manager and an image manager. That's essentially the server part of the Docker architecture. So Docker daemon or Docker engine, we use those terms interchangeably. Now, that's the server side. What about the client side? Well, it comes with a CLI, command line interface. And the CLI is essentially communicating with the Docker daemon. And typical kind of things you might do from the CLI would be maybe create an image, start up a container, um, that sort of interaction, which we will be doing a lot of. Now, on the extreme right here, I have something called a registry. And a registry is a remote uh, location where you can upload images to facilitate sharing of images. So it's essentially a remote repository for Docker images. There's nothing got to do with containers now in a registry. Containers are runtime things, so they only appear as part of the server side uh, of your Docker installation. Now, in the case of Docker Hub, so this is the architecture of Docker generically. Docker desktop application. It has the same architecture. It has a server side. It has a CLI, command line interface. It also comes with a nice GUI interface, which realistically, I suppose we use more often than the CLI. But I think it is worthwhile being familiar with the basic CLI commands, just in case you are working in a Docker environment that is not Docker desktop, but some other kind of installation of Docker. And the registry in the case of Docker is a website essentially, I suppose, called Docker Hub. Again, you may be familiar with that. So there's three parts to the Docker architecture. There's the server side, which is we often just refer to as the Docker daemon. There's the client side, which is both a CLI, which is mainly a CLI, but in the case of Docker Desktop, there's also a GUI interface. And then there's the registry, which is a remote location where you can upload images to facilitate the sharing of those images, either with other members of your team, or you may want to make it available to the global community. And there are many, many, in the case of Docker Hub, there are hundreds, if not thousands, of Docker images provided by the open source community that we can avail of. So I have Docker Desktop installed on my machine, and I started it there just before class. So, or did I? Oh yeah, here it is in the extreme right. So what you see there now in front of you is the GUI interface, which is the client side from the CLI. If I just bring up VS Code, I can type a command like Docker. Let's say Docker images will list any images that I have locally. Okay, so it's telling me that there are 3 images that I have locally, and I can confirm that actually if I look at, if I go to the GUI, and over here, if I want to list all my local images, there are indeed 3 images here. If I want to see what containers are currently running, there's one container, and if I click on it and look at its status, it's not actually running at the moment, it's exited. It's stopped, in other words. So there's only one container currently running on my local machine here. And I can actually confirm that from here, from the CLI as well. If I go Docker ps -a, I think. Yeah, so it's telling me, look, there's a container. Okay, it's status. Where is it telling me the status? The status is exited, which is what the GUI said. So, so that's fine. So, from kind of a developer or user perspective, all we ever uh, do is either use the CLI or use the GUI client side. Clearly, we can't really poke around inside the Docker, the server side of nor should we want to poke around the server side of our Docker installation. I'll just pause for a second. Probably you don't have any questions at this stage, but just in case you do, give you a chance. No? Okay. So in summary, Docker is one particular container engine option that we can use, and we will be using it to run the Docker engine on our local computers. We need to install it in the form of Docker desktop. Okay, that's where we're at. And the Docker architecturally is a client server application, and it also comes with a repository, which in the case of Docker is Docker Hub. There are other container engine options available, but as I've already said, Docker is by far and away the most utilized one. This is just summarizing what I've kind of already said about the difference between the Docker daemon, the server side, and the client side. So in terms of using Docker, then this is kind of the most basic workflow. So you've got an application, any application that you've written, could be, as I said, a JavaScript application, a Python application, a Java application. You've got an application and you want to, as we say, containerize it, or we also talk about, in the case of Docker, we talk about Dockerizing it. So you've developed your application code and you've tested it and debugged it locally. Now you want to containerize it and maybe upload the image of your application up into Docker Hub so that other people can actually download it and run it on their machines. And we can be guaranteed that they will be able to run it on their machines because of the advantages I've mentioned about containerization. So the first thing you do is you write what's called a Docker file. Now, technically, a Docker file is just a text file, but it has to be structured in a certain way. And what a Docker file contains are the set of instructions to the Docker daemon as to how it should create an image of your application. And we will look at writing our own Docker files, albeit towards the latter end of this module. I covered it earlier last year, but because there's other stuff that I think is more important for you, I've pushed it back to the latter half of the module. So it's just a file, it's a text file, but it's structured in a certain way. And really, as I was saying, what it contains are the instructions to create an image of your application. And you run that, you then kind of execute the Docker file using the Docker CLI, and it creates the image. If you want to, then you can start up a container on your local machine and tell the Docker daemon to start a container and to run your particular image inside in that container. If you want to share it, you can push your image or upload it to the Docker registry. Just mentioning the registry, actually, if I go over to my browser, yeah. So I've navigate it to Docker Hub, and you will need to create an account for yourself on Docker Hub, which I have done, and I've logged into my account. So what we're seeing here is all of the images that I have uploaded to my Docker Hub account. And most of these images are public. You can see here on the right. So anybody could download the image and run it on their machine. But of course, there are also images uh, that we can find on Docker Hub if we just go to the Explore part here and go looking for images based on either a description of them or you happen to know the name of the image. So in the case of Docker, then Docker Hub is the repository. And once you've created an image and you're happy that the runs properly when you've ran it inside a container on your own machine, you can push it up, as we say, to Docker Hub. Other people then can pull down or download the image onto their local machine and run a container with your image. And these are just some of the CLI commands that you would use to, follow this workflow here. So Docker build creates an image of your application. So when you run the Docker build command from the command line, it goes looking for a file in the current directory called Docker file, and then essentially follows the instructions in that Docker file and creates the image and stores that image locally. Now, if I check on my machine here, if I go Docker images, that's going to list any images that I have stored locally. And it looks like that there are 3 images locally. Now it happens to be that these 3 images are all images that I downloaded or pulled from Docker Hub. I don't have any image of an application of my own, not yet anyway. So there are 3 images locally, and I can confirm that if I go to the GUI interface and I go to the images part, it's also telling me you have 3 images on your local machine. Essentially, this is kind of a local repository, whereas Docker Hub is a remote repository. That's okay. So Docker build creates an image and stores it locally. Docker push, as you might imagine, uploads it. Docker pull downloads an image from Docker Hub. Docker run, that's the command to create a container. And clearly there are some arguments that you need to pass to Docker run, like which image do you want to run, and etc. Docker PS actually is how you list the containers that are currently exists on your local machine. Docker stop and stop, as you might guess, start and stop a container. This is kind of a visual, I like visuals, but this is kind of a visual representation of your kind of standard workflow. Now, the only thing I will say is from this image, just ignore this part over here. We don't tend to do this stuff anymore. So, visually what I'm trying to get across here is, okay, you're developing an application and let's say you've got a GitHub repository as your backup storage location of your application. You've created a Docker file, and the Docker file will actually be stored in your GitHub repo as well. So it'll be part of the application's code, if you like. So here's my Docker environment, okay, which is really my kind of my Docker daemon in my case, because I'm using Docker as my containerized environments. And so your typical kind of things that you might do is you can run a build command And the build command creates an image. So this is representing an image. The build command, though, as we've said, uses the Docker file to work out how do I create an image of this particular application. So I have my image here now. I can tag my image. Tagging is essentially assigning either a version number to the image or also giving it an alternative name. If I use the docker run command, that means create a container and get that container to run this image. We have docker push and docker pull. That's where you're interacting with your remote repository. So most of the Docker commits I wouldn't worry about either. We don't tend to do that. Docker stop and Docker start is about stopping and starting a container. So that's kind of just a visual representation of what I'm kind of getting at here. And really, what we need to do is just become familiar with some of the most common uh, commands that we use. So if I run this command here, docker run httpd, the run command creates a container, and here I'm specifying the image that I want used as the the uh, the body, if you like, of that container. Now, HTTPD is an image of the Apache web server, and this image is available to us on Docker Hub. So behind the scenes, what actually happens when I hit return here, behind the scenes, what actually happens is all of this. First of all, my Docker daemon is going to check, do I have this image locally? And it will find out, no, you don't. So it will go to Docker Hub and look for the image. It will download it and store it in your local repository. It will then create a container and it will load essentially the image into that container and execute the image. So let's do that. So Docker run. Now it's discovered I don't have this image locally, and it starts. Oh yeah, it's saying it's unable to find it locally, and it starts downloading it. Images are actually downloaded in layers, so it's downloading the various layers that make up our image. I'll explain what I mean by layers when we actually start to write our own Docker files, but essentially it's downloading the image anyway. And once it has downloaded it, it then goes about creating a container and it loads your image into that container and it runs the image. Now, because I've executed this command in foreground mode, uh, the terminal is, the prompt doesn't come back because um, the container is running in foreground mode. So what I could do is maybe if I open up a separate terminal and I go Docker images first, and lo and behold, I now have an image called HTTPD. I didn't have that previously, so I have a copy essentially. It is downloaded as that, and I have stored a local copy of that image on my local repository here. If I go Docker PS, which will list current running containers, there should be a container. Why isn't there a container? Let's go back to here. Hmm. Don't know why it's saying that. That's a new one on me. Let's see from the GUI perspective. This is the joys of demoing, as they say. So this is the container. It's exited. Shouldn't really have exited. Let me just try that again. So what I'm going to do is I'm going to go back to here and I'm going to select this and delete it. I pick a different image if it still complains. Okay, it's running this time. Not sure why it exited the previous time unless it's going to exit after a while now, but let's assume it's happy this time. And if I go back to my CLI, yeah, so there's um, one running image. Now, just to clarify, if you from the GUI side, when we look at the containers, there are two containers here, but this one is not currently running. Like if I click on it, you can see its status up here is exited. So it's essentially stopped, right? The Docker PS command only shows you the running images. And right now, only this one is running. So that's why from the CLI, when I go Docker PS, it's only showing me one entry. And so when it creates a container, it just gives it a kind of a name, which is really just it gives it an ID, which is just randomly generated. It also gives it a name, which is also randomly generated. Um, okay, so I have demonstrated, despite the hiccup, I've demonstrated downloading an image from Docker Hub and creating a container that's running that image. I can't really, uh, the image is running a web server. Like the obvious thing we might do is, well, if we bring up a browser and navigate to the web server that's running inside that container, you can do that. But as of now, so far, we can't because the container is isolated from the outside environment. There's ways of of overcoming that though. Okay, so the Docker run command, despite the hiccup, I mean, it should really have ran the container the first time, but for some reason it complained. So we kind of got all of this working. Um, and the contain right, so let's just move on from there, I guess. Uh, if you just want to download an image and you don't want it to create a container, you can use Docker pull command. So let's just do that. Um, try and stick with maybe with the CLI. So what I want to do is I actually want to, well, maybe let's we pull another image actually. So if I go Docker pull, let's go Nginx. Well, no, let's go Redis actually. Redis is a caching server and a database server. Again, it's very commonly used. So Docker pull now is going to just download that image, hopefully. Let's check to see if it has it locally. No, it doesn't. Starts downloading it layer by layer. And if I now do Docker images, I should have my Redis. There's my Redis image and various things is telling me the size of the image, the tag, which I haven't specified a tag. So if you don't specify a tag, it defaults to the latest. An image ID, which isn't very useful to us. When the actual image was created, only created 4 weeks ago. So it's clearly an upgrade to, because Redis has been around for quite a while. So I've just downloaded the image there. And now if I want to run that image locally, I'll just use the run command as before. This time though, maybe I'll just give it a name. Yikes. So I'm telling it the image that I want to run. Redis, I'm telling it what name, what name to give the container, my Redis, and I'll just say return. So it's starting up the image, hopefully successfully. Again, I'm running it in foreground mode, so I have to go to a different terminal to see that it is actually running. That's the HTTP container still running, so I'm just going to interrupt that. And if I go Docker PS, there's my image, which I called my Redis, and just some facts and figures. Started 49 seconds ago. Its status is running, so that's good. If I switch over to the GUI, look to see what's happening in the containers world. Here's the my Redis container. This is the first container that I started. Now this container still exists, but it's not running, as in if I go into it, its status is exited. Whereas the Redis container, its status is running. And again, you can do all of this really from the CLI as well. I'm kind of flicking between two of them, but if I want to see Docker PS, just shows me running containers. But if I do Docker PS -A, Docker PS -A for kind of all, I guess, really, then it shows you all of the containers, including the ones that are stopped or exited, as it calls it. Okay, so that was Docker pull and Docker pull really was only the new thing there. Docker push would be to upload an image. Now we'd really have to create our own image. We wouldn't be pushing up an image that we've already downloaded from from Docker Hub that we don't own, okay, so to speak. Here, I'm just saying that uh, like so far, I've just given the name that I've given the Docker images that I'm looking for are quite short, like Redis and HTTPD. But in fact, the images have what we call a fully qualified name. And this is the format of the fully qualified name of an image. But many parts of this fully qualified name are optional. And so if you leave the optional parts out, then the Docker will assume default values for them. So if I start from the left, right, the first thing you might specify when you're trying to pull an image from a remote repository is tell it, well, what repository are you pulling from? And if you, in the case of Docker anyway, if you don't tell it what remote repository, it assumes it's Docker Hub you're pulling it from. But as I've mentioned in passing, there are other remote repositories out there. Okay, so it defaults to Docker Hub if you don't tell it otherwise. If you don't tell it which user account on this remote repository does the image belong to, or which user does it belong to? If you don't tell it that, then it assumes it default as well. In the case of Docker Hub, the default user is just called library, which is kind of a generic one. Now, if you are pulling your own images, you would specify your Docker Hub username here, or if other classmates were pulling images. Okay, the name is the only mandatory part of an image name. Uh, the tag then is a bit like a version number. You could think of it, and essentially that's what it is. A tag is a version number of an image. And just like source code can have versioning, images can have versions as well. If you don't specify a tag, the default tag is latest, as in the most recent version of an image. So, for example, then this might be the fully qualified name of our HTTP. In fact, it is of our HTTP image, HTTPD image that we demonstrated. Uh, I'm gonna try and keep going, even though this is really certainly it's getting annoying for me, and I'm sure it's annoying for you, this constantly dropping out, but uh, try and keep going if we can. Yeah, so the fully qualified name of HTTP would be all of this, right? So registry, it's kind of pretty quite long with registry-1.docker.docker.io. That's the domain name, if you like, for the Docker Hub remote registry. Library is the default user where images might reside typically, though it's only images that are contributed by